So in this video we're going to talk about symmetry, and symmetry can be pretty cool. Basically, a line of symmetry is any line where you can fold the shape in half and it maps onto itself. Like, think about a heart. If you were to fold it, it would map onto itself. So a heart has one line of symmetry, just going right down the middle. But I'm not able to fold a heart this way and have it land on itself. So a heart only has one line of symmetry. For our fidget spinner here, how many lines of symmetry does it have? So it has one, if you flipped it this way. It also has one right here, if you were to flip it kind of diagonally, and one right here. So that one has 3 lines of symmetry. Be careful, this is all one line. It's not like 1, 2, 3, 4. And a circle? A circle has a line of symmetry here, and here, and here, and here, and here, and here. We could go forever. A circle has infinite lines of symmetry, which is kind of cool. All right, so first of all, just a bit of review and some vocab. What is the difference between these two pentagons? So they're both pentagons, they both have 5 sides. This pentagon is more what you think of when you hear pentagon. That's because this is what we call a regular pentagon. Regular means all the sides are the same length and all the angles are the same measure. So it's kind of even all the way around. This does not have the same angles all the way around. This is what we call concave because it kind of caves in on itself. So this is not a regular pentagon. This one is regular because it has all the same side lengths, all the same angle measures. Okay, so now that we've reviewed what a regular polygon is, this is a regular triangle. A regular quadrilateral is just a square because it's all the same lengths, all the same angles. A regular hexagon, like these are all kind of the shapes that you're used to. Just wanted to review that vocab a little bit. Okay, so now that we know what those are, my question for you is, if we're looking at a regular polygon, like a regular triangle, a regular square, how many lines of symmetry do they have? So go ahead and explore this on your own and then come back to this video. A triangle is going to have 1, 2, 3 lines of symmetry. A square has 1, 2, and then 3, 4 lines of symmetry. So a triangle had 3, a square had 4. A pentagon has 1, 2, 3, 4, 5. Basically, if you go through each vertex. Want to just take a guess on hexagon? It's got 1, 2, 3, going through the vertices, and then going through the edges, 4, 5, 6. So notice, 3 sides, 3 lines of symmetry, 4 sides, 4 lines of symmetry, 5 sides, 5 lines of symmetry. This always works. A regular polygon with just a generic n sides, just however many it has, will have n lines of symmetry. Basically, the number of sides tells you how many lines of symmetry it has. That always works. If you wanted to apply this to circles, just kind of side note, a circle has infinite lines of symmetry, and it's basically a polygon with infinite sides. Like, the more sides you add, the closer and closer it gets to a circle. So that's one way you could define a circle. All right, so let's talk about a few different types of lines of symmetry. So like the letter V has what we would call a vertical line of symmetry because the line of symmetry is literally vertical. Or a butterfly has a vertical line of symmetry. The letter H has horizontal symmetry, which means I could have literally a horizontal line of symmetry. I thoroughly appreciate that it's like V for vertical and H for horizontal, and it worked out like that, although H also has vertical symmetry, so that's kind of a bummer. Can you think of a shape or a letter that has both? Like an O. An O would have vertical symmetry and horizontal symmetry. Okay. There's another type called rotational symmetry. Basically, you can rotate the shape by some set degree from a center point and have it look the same as you did before you rotated it. For example, a hexagon has 60-degree rotational symmetry, meaning if I were to rotate a hexagon 60 degrees, just like they're doing here, I would land exactly on what I started with. So that is rotational symmetry. Like a fidget spinner. A fidget spinner also has rotational symmetry. Like if I have the center point here, what's the angle at which I would need to rotate it to get back to something that looks the same? Basically, let's think about how we came up with 60 for the hexagon. You have 360 degrees total, and with a hexagon, since there are 6 vertices, you could do it 6 times. You could rotate it 6 different times. So take those 360 total degrees, divide it by the 6 turns that we could make, and you get 60 degrees. Same thing with this problem here. If I have a fidget spinner, I could spin it 1, 2, 3 times to get back to the original. So take your 360 total degrees, divide it by those 3 turns, and that means each turn is 120 degrees. What about the angle of rotational symmetry for a regular, so like equal angle measures, it's like not crazy, a regular dodecagon, which, fun fact, that is 12 sides. So if we have 12 sides, that would be like 12 turns we could make. So take the 360 degrees, divide it by 12, and you get 30. Okay. Bit of a side note, if you were curious why we use 360 degrees, that has some pretty ancient history. There's a few reasons why we kind of speculate we used like each degree. Like in 2400 BC, the Sumerians noticed that the sun's path basically takes approximately 360 days. So like, I mean, we know now it's 365, but so they were saying like 1 turn of that would be about a degree. Also, the Egyptians had already split days into hours, but the Babylonians are the ones who divided the hour into minutes and seconds, basically, like 60 minutes, and then each minute is 60 seconds, and so that's 3,600 total. Basically, they liked the number 6. They used a lot of 6s in their calculations. Today, we typically use 10s, but that's not always the case. But basically, 360 just popped up a lot back in the day. Okay, one final piece of symmetry that I want to mention is point symmetry. Point symmetry is a form of rotational symmetry, but it's if you can rotate the shape exactly 180 degrees from a center point and get back to the same thing, then that is point symmetry. So it's a specific type of rotational symmetry that's exactly 180 degrees. For example, the letter N, if we put our pencil right in the middle and we spun it around 180 degrees, we'd get back to the letter N. So the letter N has point symmetry. Can you think of another letter that would have point symmetry? If we do like the letter R, the letter R does not have point symmetry, because if we rotate it 180, it's not going to be the same. But the letter O would work again, because rotate it 180 and you'd get the same letter. nature is all about symmetry, which I think is really cool. There's a lot of just geometry in nature. Think about like orange slices or starfish, snowflakes, leaves, flowers, spider webs, and even humans are like very symmetrical, especially like a vertical line of symmetry there. So I just think that's pretty cool. Here's something I saw on the internet, if you want to read that. Maybe you enjoyed that, I don't know. Symmetry jokes.